So good morning. I hope everybody's awake. We've got a lot of interesting talks. There's a lot of stuff I can take with me, at least. The Rocky cheat from Victoria presented was quite astonishing to me because I wasn't aware of it, even being for a long time in project management. So it looks like I'm a little bit behind. Anyway, as I said, good morning. I have a question before I'm starting really diving into embedded systems. Who's doing C and C++ development in that group? 1, 2, 3, 4. Okay, a few. Who's doing embedded? Just a few. Okay, so everybody else, grab your coffee. Because we're going to talk about embedded. I mean, we learned a lot about what is the current trends in technology. We're going to AI components. We're going to computing, offloading, and so on. We're connecting to the cloud. How are we going to handle that in the car? There are a lot of devices coming in the near future to us, which really are not connected. They're not IoT devices. Whatever limitations they have, might be power consumption, might be they're driving on the road. And those cars actually need that computing power within the device itself. And that's actually what we're looking into. So let's see. A few words about the company itself. Of course, also we were founded in 2014, so some might consider us as young. As a spin-off from the RWTH in Aachen, so a couple of scientists, researchers, started in 2014 thinking about a larger problem than what they did in his PhD, and they came up, well, let's solve that problem, and that is how the whole thing kicked off. 3 founders. In the meantime, we reached a threshold of 60 employees, so we are quite growing fast. We are already present actually in APAC. We are present in Israel as well with an office, and in the US. So I think that's quite remarkable. Talking about the company itself again, basically the customers we are already dealing with and which are somehow considered to be on our pipeline, you see the who's who in the market. As my personal background is in automotive, of course, I'm a little bit emphasizing on that one because that's where I have most of my experience. So I got learned actually that I should start a presentation with some wise words because that increases trust. So look what he said. I mean, it's a little bit out of statement, but the key point is, I think everybody's good in doing puzzles. Anyone weak in doing a puzzle? Or no? Have you tried that one? That is an area of 5 to 5 on each side. I tried it, and I failed. Miserable. So that's the reason why I'm not changing it, because I'm not able to put it back on the same kind of, right? But that's really what we're dealing with. We're reaching another dimension of computing. We are combining FPGAs, DSPs, multiple CPUs, actually multiple cores to be more precise, whatever AI component is coming in the future, and that all talks to each other. Can you predict how the power consumption is, bus latencies, and all that kind of stuff? What are the dependencies running multiple threads on multiple cores sharing the same variables? That is not handled. You can't handle it by a spreadsheet anymore. That need to be really something you need to calculate, to compute. If we're going to use AI in the future for that, I think that is an interesting question. I don't have an answer on that, but I think it's really, when you're talking about data, I mean, those systems creating data like hell. And it's going to be interesting, actually, finding out if there is an AI algorithm or way actually looking at the data which unveils things we haven't even seen by today. So looking again, basically, on Silexica, what is the unique value we're currently doing, actually? It's basically it's application analysis. So what we're analyzing for is actually the semantics. So we try to understand what happens static in the static code analysis, and at the same time, what happens during runtime. Just giving you an example, you have a pointer. It's quite easy if you use standards like MISRA, because then usually you're not changing your pointer during runtimes. If you're more advanced in C++, you might have a class, and that changes over runtime. So you don't really know where the pointer is pointing to just while you're executing it, and not before. And this is actually the starting point of all the analysis we're doing. Was that the wrong button? Okay. So the devil's in the detail. So we're using C, C++, of course. There are multiple libraries. There's even code now in a car, for instance, which hasn't been developed by the OEMs anymore or by the tier ones. That's an interesting combination. I need to give reliability and also applying safety rules for code which is not under my control. That's an interesting question, how you're going to do this in the market. So, however, all that ties back to the point, basically, we got different kind of internal states we have to deal with. There is stuff like schedulers when you're looking for AUTOSAR, typical classic systems. There's multiple inputs for computation. Timing behaviors, it all falls in the same thing on this multidimensional cube. So, long story short, I think it's a time for new tooling. The old linear way we're doing actually software development, especially when I'm looking back 20 years ago, I think it's not something we can carry forward for the next generation of computing. And this is where we're looking into. However, starting point is source code analysis. Let's look a little bit of what we really have in our portfolio. So it's, for instance, for C and C++ analysis. We know the challenges, we know the benefits. The code understanding is key, basically, what we're doing. There was recently actually an announcement, or actually a kind of a research going on where usually developers spend most of their time. And I hope anyone can disagree or agree. I'm really glad getting that feedback. But the report somehow unveils that we're still spending as developers quite a lot of time on finding where, how the code behaves and interact to each other. So we are not focusing on, well, this is my problem. This is how I'm going to solve it from the algo point of view. Usually we try to identify where do I need to fit it in and what's going to be the impact. So the understanding of that impact on the dependencies seems to be key to do in a very professional way the job. And the most advanced guys in the job, the senior guys, usually they know the application by heart. And I worked as a consultant for 10 years. So I jumped into projects every time it was burning, basically. It was already out of control. And then you got this 100,000 files saying, we have a problem, timing, typical problem in automotive. Can you solve it? Okay. And it starts actually really analyzing the code, who's calling what, and so on. And this is really what you need to analyze while you're running the code. So what are the ingredients actually for deep source code analysis? It is, of course, help me to understand what really happens during execution. So what is my call graph? And not on the static way, on the dynamic way. On the other side, you try to get some kind of profiling information to understand actually where you spent your time. So a call graph doesn't indicate actually if that function called just once in my lifetime, or is it actually the one which is a hot spot where I'm spending actually 80% of my time in. So maybe that's worthwhile to consider. Another ingredient, of course, is when you're running code is thread and variable analysis. So you have two threads running in parallel on two cores. Unfortunately, usually they are sharing as well variables. What happens if both try to access it at the same time? Either one or the other needs to wait. That works quite simple with one variable. When you look to the typical applications I'm dealing with, we're talking about 65,000 variables, 100,000 variables. Can you identify the one which might be worth to think about it? No. So again, analysis. So that's the other ingredient you need to have for that. And the third thing, actually, the final thing on that ingredient is, of course, having understanding what happens timing-wise. So what is the scheduling you're applying to it? That can be for classic AUTOSAR systems based on formerly known as OSEC, can be basically the static scheduler. It's getting more interesting when you're looking actually to AUTOSAR adaptive kind of applications or C++ on a Linux system. It's getting even more tricky because the scheduling is not really predictable anymore. CFS is quite a beast on that level. So you need to extract that kind of dependencies to understand really what's going to impact if you change it, if you set up a higher priority on the thread or stuff like that. So I give you a couple of use cases where we believe actually that information is valuable, and you might agree or you might disagree. I'm open-minded on that. So we got this code understanding. It's all about visualization. I think it was Victoria said that in the beginning. Help your client to understand what he's dealing with. That is really important. Because if he can't visualize the problem and you can't visualize the problem, what the hell you're talking about? So try to nail it down to a point that everybody says, I agree. This is what we need to solve. And I think that's part of the visualization story. There's certain kind of metrics you can apply to code looking at it from a logical point of view. There's logical line execution. So what is my code density? How am I going to measure it? That's an interesting question. If I'm a developer and I have to focus on the functionality, solving a problem, whatever it's going to be, I try to understand what is the ratio here. Is it a one-liner function? Versus is it a 100,000-liner function? What's going to be the data utilization? How many data inputs do I have? How many outputs do I have? I'm writing back on the structure, stuff like that. These are causes for errors. There was recently a talk about C++, which has the approach actually that in a single file are only 50 lines of code, and a function is only supposed to take 2 parameters and 1 return value. And a function basically has only 1 level. I was looking at the code. It's understandable, but don't ask how many files you have. It's going to be an endless amount of files. But it's all about simplifying the problem instead of making it overcomplicated. And as you have many more, or more actually, input parameters in the function, of course, the risk in running into a miscomputation or in a problem on the interpretation of the values is increasing dramatically with the amount of variables you have. Stack size is another topic. Function arguments, as I said before. 2 are good to handle. 10, 15, or even more, especially on automatically generated code, it's getting quite nasty. Recursion candidates, right? That's another topic you might be interested in. Function pointer usage, callback functions, variable propagation. That's an interesting topic. Everybody knows debugging, right? GDB and that kind of magic. You're having that breakpoint hit, you did well. How does the value you're seeing actually in one of your parameters, who is actually contributing to that value? When you have a call stack of 50 functions, let's say, try to identify which one recently changed your variable that you've seen, for instance, a character like A. You're starting with a set and you're asking yourself how I'm ending up with A. So who's contributing? Value propagation is one of the key features, right? So complexity, intensity, we talked about that. Read-write of bytes, that's another hot topic we're constantly seeing. Runtime memory stability, obtaining memory, releasing memory of call, and system call count. So, by the way, who's in automotive and AUTOSAR adaptive-like systems? Hey, cool, I love it. I think we're all seeing that on AUTOSAR adaptive that it's supposed to be based on a Linux system. On top of that, actually, we're seeing the kind of services provided, which is a little bit similar like what Julian explained before with the kind of service providers and stuff like that. How are you going to ensure reliability on that? Is that something you can certify? And there's code you actually even haven't written, and you're trying to use it. If that is relies or ties back actually to ASIL level, to automotive safety integrity level, it's going to be really interesting if you're going to get a stamp on that. So system call, and this kind of dependencies between kernel, user space, and other services provider, I think it's going to be key to understand in the future how the whole application should work. So that's again the variables. We talked about that. It's just, visualization. We talked also about that. That's the kind of dependencies you have on variables. Talking about synchronization, time. We had it yesterday. We had a short talk with one of the guys and said everything I did within the last 30 years in my business was related to time or physics. I don't understand why students are not more pushed on physics, because time is key to it. If you're talking about pressure is meaningless unless you're talking about the time you're putting up the pressure on it, right? If you talk acceleration, positive like negative, it's all about time. So time is key for everything we do. Even on the business side, time to market, right? So time is key to it. How can we ignore in an application time? Someone tells me there's an application which is really independent of time. I hardly can believe it. Maybe on the server world, That might be the case. But everything else is somehow tied to physics, to real-life application, IoT devices, edge devices, whatever you have which interacts with the environment it's currently located in is physics, key to it, and therefore time. So what we're identifying is actually that kind of synchronization point. So we got multiple threads. We shared variables. So where are the points where the variables are actually accessing from A to B to the different threads? So where do I need to pay attention to? Another thing is what you can generate out of that is some kind of statistical data, giving you an impression on how good you're doing. Good is not meaning you're failing. It means just, do you have an understanding of the ratio you have actually between synchronization and computing power? Do you know that actually what really happens in your application? Control flow versus data processing time and stuff like that. The time you're spending in your application actually versus you're using actually third-party code. That kind of dependencies. Shared variable access, blocking synchronization issues. You got a semaphore which is not released and stuff like that. So that's the analysis part. Now the key question is, what are we going to do with that? I mean, it's a little bit like the data mining story we heard today. You got tons of data. If you don't know what you're going to do with that, it's going to be meaningless, right? So what we're doing actually is with that data, and that's just an example, that's the direction we're taking now, is, for instance, helping you on code refactoring. Why code refactoring? We just recently learned that FPGAs is increasingly getting popular. But it was always popular, to be honest, at least for a technical point of view. But there are also, if you look actually to the Xilinx story, or also Intel story on FPGAs, you see that they're more picking up on this AI part for embedded. That can be edge devices and IoT, that can be the car, wherever. So from that point of view, how you get actually this AI into an FPGA? Do you want to do that in actually in VHDL? I think it's going to be somehow a little bit a tough ride. But from that point of view, there's a cool way of doing it. It's called high-level synthesis. It takes actually a C-like input. I'm not claiming it's equal. It's 100% C. You got limitations to deal with. But as a result out of that, you can straight put it on the FPGA with a tool chain. Vivado, for instance, SDSOC, stuff like that. So looking at that code, had anyone done HLS on C for, okay, so you have no clue what I'm talking about. C to FPGA to hardware, period. C is a language which is not made for parallelism per default. So how do I going to tell my C code that that loop, for instance, makes sense to be parallelized? I need to tell it as a developer because I know hardware, I know software. And I can tell you for a project you have maybe with 100,000 lines of code, you don't know where to unloop a role, where to parallelize. That is where we're actually using this analysis data. So we're helping you with that. Based on the analysis we did, we can actually tell you exactly that loop makes sense to unroll to factor 4. Or that statement can be parallelized, so you can have 16 instances of that running parallel. That gives you that kind of improvement, because you understand the code. So another thing is actually giving you hints and tips on, for instance, from C to C++. You're analyzing the code, you see where your bottlenecks are, and based on the experience you have on executing the code and the timing, you have a pretty clear picture on does it make sense actually to transform that statement, for instance, into a C++-like statement, or is it more performing in a better way? For instance, a printf versus a cout, or an array versus a list. These are just examples. You can also have some kind of user-defined logging. Again, it's all based on the analysis you're doing. It's just examples of what you can do with that data. Diving into a little bit more deeper on the FPGA side, but I don't want to get you bored on that, is just outlining basically the kind of workflow. You're analyzing your code, but actually you're getting some kind of high-level performance estimation, which gives you a hint, actually. Does it make sense to put that, offloading that function in hardware, or doesn't it make sense? So you try to define actually a computing hotspot, and then basically handing it over to the next following tool chain, which is usually provided by Xilinx, or especially the FPGA vendor. So that's a high-level point of view. Transformation guidance, another topic is, for instance, multi-thread synchronization, data structure optimization. So looking at the cache system in the CPU, when you have a structure which, for instance, contains 16,000 entries, it might be worthwhile to consider the order of this, because if you have certain access patterns, you start to identify that this is, and you cross the cache size limits, or the lines actually on the cache, it's going to be a dramatic slowdown because it's not going to be cached anymore. So that kind of stuff we can also identify with the analysis we're doing. Pipeline parallelism, you just name it basically. I'm skipping that one. It's architecture model because I think we're now getting to the final point, because I'm also need to keep in mind the time ticking. Talking about system behavioral simulation. So you got a hardware model. You got a development team A and maybe multiple development teams somewhere located spread around the globe. How are you going to predict the behavior of the hardware, actually of the software on your hardware? So usually what happens, what we've seen very, very often is actually you got a team, for instance, located in Romania. You got a team in Germany. You got a team in the US. Everybody is doing software for the same kind of hardware. Then they try to integrate. And guess what happens? It's not working as expected. Everybody had the specification. Everybody was fulfilling the specification he had. So there's no one you can blame for. Specification was done with the best effort and the experience the people have in that field, but it doesn't run as expected. Because there's no way on the early stage already to check out and to verify that this is really what's specified is really working on that hardware. Usually that specification is written based on the data sheet which is provided by the semi-vendor. So what we are already generating is based on a hardware model is like task states and Gantt charts. Looking a little bit in the direction we're going, and now we're talking about the outlook, is we're actually working on analyzing the power consumption of the entire system. So if that goes to computing, if that goes to an FPGA, that's going to be the impact you have actually on the power consumption. What is the advantage of using, by the way, hardware FPGAs? Any clue? It's predictive, timing-wise. Absolutely predictive. So if you have 4 nanoseconds from the input to the output, it's always 4 nanoseconds. Not plus, not minus, 4 nano. That's one point. The other point is basically, and that's even more important, constantly power consumption. There is no impact during runtime that power consumption goes up, like on the CPU load, or goes down. So that means you know from the point you're starting on, my FPGA is going to take 1 milliwatt. And that's it. On the CPU, it's hardly to predict actually what's going to be the power consumption unless you're editing a power schema and so on. So power analysis insights is on our roadmap. And then actually taking that further to the next level is the communication link utilization. So I have a bus in my system. There are multiple cores on it. There's memory on it. There are other components like peripherals on it. What's going to be the utilization of that bus? Is that something which just randomly shares a little bit of variables, or is that heavily occupied because I'm transferring, for instance, a video stream, which doesn't really make sense, but transferring that to over the bus system. So, of course, I mean, everything needs to wait until that frame has been processed. That's the kind of stuff we're looking into currently. Long story short, I have a few other slides afterwards, but got 4 minutes. It's all about analysis. That's a kind of data mining on an embedded system. What we can develop out of that is giving you the guidance, how to make your system smart. And finally, of course, with the guidance you have, you want to simulate. Does it help me? Does it solve my problem? Can I predict my behavior? And this is actually the kind of threefold magic, I would say, Silexica is looking into. It's analysis, guidance, and simulation. So that is a typical system you're currently seeing in embedded. It's, by the way, it's very close to an Audi A8 system. You got a high-performance cluster. So you got, for instance, 4 A53 cores. You got an FPGA type of thing, logic, sometimes already using DSPs, for instance. You got a safety part of that. So there is a R7, R5 core, when you're taking Renaissance as an example. There's a core on it basically which is dedicated for out-of-the-box classic applications, ASIL level and stuff like that. And deep learning coming not in today. What is interesting actually, all those actually communicating over the same bus structure. Of course, you got crossbars in the chip and stuff like that, but at the end of the day, they're really sharing the same data on the system to the same bus. So that means processing of large packages might be actually harming your performance. And that is the kind of stuff actually Silexica is looking into from a point of multi-application behavioral systems. They've got multiple applications being combined on one hardware. What's going to be the impact? We talked about timing. We talked about power consumption, communication link utilization, stuff like that. And that is a little bit the future we're looking into, is how to create, you mentioned multiple inputs. That isn't embedded really the case, right? Every semi-vendor, every chip has a different trace format. It's not that you have a common standard on that. So sometimes you need to deal with real traces coming from a real hardware. Sometimes you have actually software traces which are created by totally different tools. Software models, binaries, there's a new kind of standard called Almatia, it's popping up, Bosch is pushing for it, quite interesting. I find it personally very exciting. And even sometimes you have Excel sheets. How to bring that together on one single platform. This is the future we're looking into. This is actually where Silexica is going for. And that is basically the end. Oops, sorry, that one. Thank you very much for your time.